All right, so we have this archer pulling her bowstring back 0.4 meters by exerting a force that increases from 0 to 230 newtons. And then it's being pulled back a displacement of 0.4 meters. So let's look at B first. I want to talk about part B. How much work does the archer do in pulling the bow? The number one mistake for part B is to go, oh, they're asking for work. Okay, work equals force times displacement. So the force is 230 newtons times 0.4 meters. What's the mistake there? Is the force of the bow constant? It's not a constant force. So look, before the bow is stretched, what's the force in the bow right there? The force of the bow is what? 0. It's not exerting any force, right? Now what happens to the force of the bow the farther back she pulls it? So when she pulls this bow back, what happens to the force the farther she pulls it back? The force gets greater. It works the same way as a spring, It's elastic. So instead of calling it force of spring, some books call it force elastic because springs are elastic, bows are elastic. So here's how you want to think about it. So the force of the bow increases from 0 to 230. So how would we solve part B? How much work does the archer do in pulling the bow back? Well, on a force displacement graph, how do you find work? It's the what? It's the area, right? The area under this graph, you're going to go 1/2 because it's a triangle. The base is 0.4 meters, and then the height is 230 newtons, right? So basically, when you really think about this, all you're doing is, you're using this equation, but you're using the average force. The force here is average. What's the average of 0 and 230? What is that? My brain's off. That's going to be 115, right? All you're doing, and that's what this 1/2 is all about. This 1/2 is giving you the average force. Does that make sense? So we put a 1/2 in front of here. That's going to be the work that she did, and this comes out as 46 joules. Okay? That's the work done, 46 joules. Okay, how do we do part A? To find out the spring constant, how do we do that? Well, for part A, you're using the equation force of spring equals K delta X. Yes, I know, technically it's negative. The only reason it's negative is the force is opposite the displacement. I'm just going to leave it off. So look, we're solving for K, the spring constant. So spring constant is going to be force of spring over delta X. So look, when the spring is stretched 0.4 meters, when the bow, when the bow is stretched 0.4 meters, what's the force? 230. So this is going to be 230 newtons over 0.4 meters, which gives us a spring constant of 575 newtons per meter. Now, I want to show you one other thing, because this is cool. One other alternate solution to part B. So we already have the answer to part B. Simple enough. It's the area under the graph. But I want to show you one other way you could have looked at this, because it'll help you understand this chapter. Another way you could have solved part B to find the work done is you could have gone like this. Mechanical energy initial plus or minus work non-conservative equals mechanical energy final. So let's list this all out. So we have kinetic initial plus gravity initial plus spring. Well, actually, is it a spring here? No, it's a bow. Let's call it potential energy in the bow initial. Now, is the archer, is she a non-conservative force? When she comes up to the bow and starts to pull it, is that conservative or not conservative? That's not conservative. Remember, if it's not gravity and it's not a spring, then it's not conservative. So we're going to say, now, is she adding energy or removing it? When she pulls on the bow, is she adding energy to the bow or removing it? Is this going to be plus or minus? Plus. This is going to be plus work of the girl. Equals, okay, what's mechanical final? This is going to be kinetic final plus gravity final plus energy in the bow final. All right, before she starts to pull the bow, is there any kinetic? No. Is there any potential of gravity? This whole problem's taking place on the same horizontal surface, okay, or the same horizontal level. Before she starts to pull the bow, is there any energy in it? No. Okay, then she does work, right? Then the girl does work on the bow. She pulls the bow back. When she has the bow all pulled back, is there any kinetic yet? Nope. Is there any potential of gravity? Nope. Is there energy in the bow? Yes. So look at this. The work done by the girl in loading the bow, what's the equation for potential energy elastic? 1/2 kx squared. Get ready to be amazed. What was our spring constant? 575. What's the x? How far did she pull it? 0.4. Guess what we're going to get? 46 joules. So you also could have done that. The work done to load the bow is equal to the potential energy stored in the bow. Or you just could have found the area under the graph. Okay? There's more than one way to do a physics problem, typically.